I'm going to try to keep the videos fairly short for this lecture. This is the last lecture for Unit 2. The Unit 2 exam's coming up. And to close things off, I'd like to tie it all together. And we're going to tie it all together with what we call rovibronic spectroscopy. And I've actually added an extra set of notes as well to the Blackboard site to support this, because I didn't think we were going to have time to get to it. But it nicely ties everything together. Rovibronic is what it sounds like. We're going to include rotations and vibrations together. And I'd like to get you to become very comfortable with this bracket notation of states, where we identify a specific quantum state by its set of quantum numbers. And you always have to remember that that also corresponds to a specific wave function. And we'll deal with this more later, but we've been talking about vibrations of molecules and rotations of molecules, and it follows that we need to be able to describe both of those things simultaneously. So there's an overall wave function for a molecule that's both vibrating and rotating at the same time that we can specify with three quantum numbers: a vibrational quantum number V, a total angular momentum quantum number L, and a total z orientation of the angular momentum m sub z. So we're going to have this bracket, the bracket with three quantum numbers, VL m sub z, specifies a state for the molecule. So in spectroscopy, we absorb a photon, and we're going to go from an initial state to a final state. And we have to change the energy, and the change in energy has to be equal to the energy of the photon, and we express all that in wave numbers these days. So we're going to go from this initial state to some final state, which will have a final set of quantum numbers. And all of those quantum numbers can change, and the question becomes exactly how much do they change. So on the left we have the initial state, on the right we have the final state, and we specify it by these quantum numbers. So the next thing is, if the final quantum number for vibration is equal to the initial quantum number for vibration, therefore there's no change in vibration quantum number, that's the pure rotational spectroscopy we just addressed. So nothing happens to the vibration, and we just get pure rotation. We actually almost never get pure vibrational spectroscopy. We'll get to that in a second. But we looked at the big picture vibration spectroscopy for a reason, which I'll also touch in a second first. So the second thing is, if the vibration quantum number changes, then the rule is that it's going to change by 1, and to keep things simple, we're going to think in terms of absorption spectroscopy. So the energy needs to be going up, and so the vibrational quantum number has to go up, and it turns out that it just has to go up by 1, exactly 1 in the harmonic case, which is mostly what we're going to worry about here. So the change in vibration quantum number is going to be 1. So now, the energy of the photon, the wave number of the photon, is equal to the wave number for this state that's specified by quantum number V plus 1, which is the final vibrational quantum number, and then whatever the final rotational quantum numbers are, LF and MF in this case, then minus the energy and wave numbers of the initial state, which is VI, LI, MI. So again, the energy of the photon is equal to the energy difference of the two states, the final state minus the initial state when we've absorbed a photon and we're doing absorption spectroscopy. Now, we need to introduce what spectroscopists call the full term of this state. So and this is going to describe the wave number energies, and we call it S, and it includes the vibration quantum number and a rotation quantum number, which oddly enough we're now going to call J, and basically J and L are the same thing. And so this is G of V plus a half, and then plus this thing we're going to call F of J. There is a reason why we use J instead of L, and it's more of an issue with larger molecules than diatomic molecules that we're not really going to spend much time with here. So just bear with me. It's what spectroscopists do, and we can use them interchangeably here. So I just kind of want to introduce them to you, and again, if you're to read anything about spectroscopy, you're going to hear about J as a rotational quantum number, so we may as well introduce it now. So we have G and F, and that term is going to describe the wave numbers associated with the energy level. So it's the wave number version of the energy level expression. It's exactly what we want. And it only depends on J. Remember, M sub Z, the orientation quantum number, has nothing to do with the total rotational energy. So that's approximately equal to the vibration wave number, the characteristic wave number of the vibration, times the quantum number V plus a half, plus the B value, which we're going to specify is associated with a particular quantum number V, but basically it's a constant, times this quantum number J times J plus 1. So that's the vibrational part, and it's of order 1,000 wave numbers, and this is the rotational part, and it's of order 1 to tens of wave numbers. So the vibrational number is much, much bigger, and this specific case is for the harmonic rigid limit. So we're not going to, we'll talk in class a little bit about this, what happens when we relax that, but we can understand the basic features by asserting that the molecule is harmonic, and from the point of view of rotations, the spring is stiff enough that it's perfectly rigid as well. Okay, so that's how we're going to treat this here. So now the fourth thing is that if the vibrational quantum number changes by 1, the total energy is going to go up for sure, because that vibrational energy is just much bigger than the rotational energies. Remember, the vibrational energy is thousands of wave numbers. The rotational energy is just not that big. So total energy is going to go up. We've taken care of that, and we have to have the total energy go up if we absorb a photon. But this has an interesting consequence with regard to the change in the rotational quantum number. Now the other thing is that we need to conserve the photon orbital, this photon spin angular momentum, when the photon blips out of existence. So that spin of 1, actually it has, like any thing with 1 unit of rotational angular momentum, the orientation of that spin can be +1, 0, or -1. So there's 3 different values allowed for an orientation spin quantum number. We call M sub S, just like we call, we've been calling M sub Z the orientation quantum number for rotation. So M sub S can be -1, 0, or 1. There's 3 values allowed. And so it may not be surprising that it turns out that the change in M sub Z of the rotation of the molecule can be -1, 0, or 1, because that's basically how that orbital angular momentum, the spin angular momentum of the photon, it can be conserved as the photon disappears into this molecule and adds to its energy, and also matches its angular momentum into the rotation of the molecule. Now the bottom line is this means actually that the rotation of the molecule can go down by 1, stay the same, or go up. Those are all valid, because the overall change is still a very large increase in energy because of that increase in vibration quantum number. So the vibrational energy goes way up, and we can basically give a little bit of that back by reducing the orbital angular quantum number by 1. We can also keep it the same, and we can also increase it by 1. We have to change M sub Z by 0, -1, or 1, because of the need to match that M sub Z value, the M sub S of the photon. But we can actually get that done with any of those 3 changes in the orbital rotational quantum number of the molecule. So that makes it a little more interesting than the pure rotational case. We can play around with this a little bit more. So, by the way, 0 is only allowed sometimes. We're going to get to that more later. But so plus and -1 actually basically always goes, and then 0 is kind of a special case. Now, also note that the amount of energy associated with the vibration change is always V naught. So we go from V to V plus 1, and we know that the harmonic vibrational energy levels are separated by always exactly V naught in the harmonic case, which is the limit that we're addressing here. So that's exactly V naught, or wave number naught, twiddle nu naught, excuse me, is the change in the vibration energy. And now we're interested in the smaller change in the rotational energy. Okay, so first, if the the J, or the L value, goes down by 1, then the change in the F part of that term, the rotational part of the term, is going to be negative 2b times the initial J. So down by 1, we're going to go from 1 to 0, or 2 to 1, or 3 to 2. And so the initial J has to be at least 1, because you have to have somewhere to go down to. And the total energy is going to be slightly lower than the vibrational constant wave number twiddle nu 0. So it goes down a little bit by 2b times the initial J value, the initial orbit, the initial angular momentum quantum number. Now, if the change in J is 0, then there's no change in the orbital quantum number, and that can be true for any rotational angular momentum quantum number, because there's no change in it. But this is only valid if that change is allowed, and again we'll get to that. And finally, if J goes up by 1, then the change in the orbital, the angular momentum term, is plus 2b times J plus 1, and the initial J plus 1 again, can be 0, 1, 2. You can go up from the bottom, up from 0, so we can allow 0 here. And the total energy, the total wave numbers, are going to be slightly higher than just the wave numbers associated with the vibration. So that means the first one, where J goes down by 1, we call the P branch. The second one, where J stays the same, we call the Q branch. And the third one, we call the R branch. So in total now, the photon wave number, which is equal to the change in the total term, is equal to the wave numbers of the vibration minus 2bj initial, J1, 2, 3, 4, 5, etc., for one case. It's also equal to just the nu of the vibration for the second case, and it's equal to the new vibration plus 2bj plus 1 for J initial equals 0, 1, 2, 3, etc. So there are three possibilities for the sets of wave numbers of photons, for the photons that we can allow for this rho vibronic transition. And again, this is the P branch, the Q branch, and the R branch specified by this. So this is cool. When we allow the molecule to vibrate and rotate, we see that we can, if we absorb a photon, the total energy has to go up. But and really it means the amount of energy in vibration has to go up. But the amount of energy associated with the rotation can either go up a little bit or down a little bit, and we get a whole succession of possible solutions based on that.